line drawn perpendicular from the center of a circle to a chord bisects the chord. That is the theorem, theorem 1. The line drawn from the center that is perpendicular to the chord. So the line drawn perpendicular from the center of a circle to a chord bisects the chord. What this means, it means the following. A line that is drawn from the center of the circle perpendicular to the chord. Let's say this is the chord. A line drawn from the center of the circle perpendicular to the chord. That line bisects the chord. Let's say the chord is called AB. Let's call this chord AB, and where they meet is point C. This theorem is also known as the perpendicular bisector. This theorem is also known as the perpendicular bisector theorem. If you hear people are saying perpendicular bisector, this is the theorem that they are talking about. Some people would just say perpendicular bisector just to sound nice and all of that. And this is O, of course, the center. A line drawn from the center, drawn perpendicular from the center towards a chord, meaning it forms a 90 degrees, it forms a right angle with the chord, that particular line. The claim is that this line bisects the chord. So let's look at the theorem, and in the theorem we're going to look at the main clause and the subordinate clause. So what we are actually trying to prove is the subordinate clause. So here's the main clause. The main clause says the line that is drawn perpendicular from the center of a circle to a chord. So there's that truth that there's a certain line that is drawn perpendicular from the center of a circle to the chord. Then there is a subordinate clause. The subordinate clause starts here from this verb, bisects the chord. The word bisect means to cut into two equal parts. It intersects, but cutting into two equal parts. This is also known as the line OC is forming what we call the midpoint there at C. It's forming a midpoint there at C because a line that is drawn, it bisects the chord. So meaning C becomes a midpoint such that BC is equals to AC, or AC is equal to BC. So what we are required to prove here, RTP, we are going to prove that AC is actually equals to BC. Given that OC is perpendicular to AB, then we are going to prove that AC is equal to BC, because they say it bisects the chord. As we prove, the first thing that we are going to do, we are going to construct. We are going to construct by joining. This is our proof now. We are proving now. We are constructing by joining OA, and we're also going to join OB. So we are going to join OA, and we are also going to join OOB. So we are joining OB now. We are joining OA now. So you will realize that OA is a radius and OB is a radius. So in plural form, they are radii. Other people say they are radii. My accent, or my pronunciation rather, is such that it's a radii. And we construct that such that is true. OA become OB. Remember, if they are radii, definitely they are equal. At some point in time, we have to say OA is equals to OB, because they are radii of a circle, of the same circle. So radii of the same circle, ladies and gentlemen, radii of the same circle are equal. Let's do this. In triangle, which triangle? OAC, and we're working in triangle OAC. Can you see that triangle? And we're also working in triangle triangle OBC. OBC, not where they sell meat. Not where they sell meat. There's an OBC shop where they sell chicken and all of that. Not that one, of course. Triangle OAC and triangle OBC. The OBC, the triangle at this at this particular point in time. Ladies and gentlemen, in those particular triangle, what is happening? In triangle OAC and triangle OBC, what is happening? That's what we are supposed to do first. Well, what is happening in these two triangles? It is true that OA is equals to OB. OA is equal to OB, and the reason is because they are radii. According to some of you, they are radii. It is true. Also, it is going to be true. Remember, we're given that the line drawn perpendicular. The line drawn perpendicular, meaning that 90 degrees, we see that there is a 90 degrees there. So we can call those two angles, those two 90 degrees at a point C, we can call C1 and the other one C2, of course. Therefore, if we have declared that is C1 and C2, we can therefore say that angle C1 is equal to angle C2 is equal to 90 degrees. And the reason that is, it's because this was given. This was given that these two lines are perpendicular to each other, meaning they form 90 degrees. Also, OC is actually equal to the very same line OC, meaning the OC in the triangle OAC, the OC in triangle OAC is equal to the OC in triangle OBC. If you were to make those there's triangle AOC, and also there's triangle, you see. So the OC is equal to OC. And the reason for that, it is, it is what? Ladies and gentlemen, it is common. Okay? It is common. By means of these three truths that we have found right now, ladies and gentlemen, then it does mean that this triangle OAC and triangle OBC, it qualifies to be known as, therefore, they are qualified to be known as triangles that are congruent to each other. Therefore, a triangle OAC is congruent to triangle, which triangle, ladies and gentlemen? Which triangle? Triangle OBC. And why are they congruent? Because there is a right angle and a hypotenuse and one other side. That is your reason, RHS. Your reason is RHS. And therefore, since these two triangles are congruent to each other, it does mean if triangles are congruent, what happens is that they are equal in each and every way. They are equal in every way possible. What does that mean? It does mean that really, indeed, therefore, AC is equal to BC, and that particular theorem happens to be a proven theorem. Therefore, that happens to now be a proven theorem. Ladies and gentlemen, that is the proof of theorem 1, perpendicular bisector.